All right, welcome everyone to this week's Ronin seminar. This time we got Vesselin, and I feel like I should have practiced pronouncing your last name first. Gueorguiev?
Close enough?
Close enough.
Yeah.
All right, that's a win. All right, who is going to talk to us about quantum computing, and hopefully for the majority of us who know that only by its name will give us some insight as to what's going on there. Take it away.
Thank you, John. Yes, and I'm glad that I can present some of the things that I'm passionate about. And this is something that would come soon to be one of the very high-tech industries. So I'll talk about quantum computing, and since I'm aiming at the general audience, basically it would be a little bit of historic overview, and then I'll go into resources and what is the current status. So, as I said, brief history of computing, and then since we have to merge into quantum computing, which is related to some fundamental understanding of physics, then will be outline of a brief history of physics. Then I'll go into key concepts in quantum computing and possible applications of quantum computing. Then I will make an overview of current quantum computing resources, what is out there, and of course there are other things that could be out there that I'm not aware. But I just want to make the point that it's out there and it's available for people to play and explore. Then I'll outline the problems and future directions, basically where people can look for opportunities. And then I'll end up with open discussion. So it was amazing to go in the internet and dig up information about computing. So interesting enough, I mean, the history of computing is really old, about 2,000-3,000 years. This is Roman kind of replica of Sumerian abacus. Then we have some artifacts from about 100 BC, which is presumably ancient Greek astronomical analog computer. Now, important point is that until the Middle Ages in Europe, the Latin symbols were used for numerical kind of calculations and in numerical work, conveying information about numbers. And the Latin symbols are not as convenient as the Hindu-Arabic system. So actually a big push into development of math and computing comes with introduction of the Hindu-Arabic numerical systems in Europe. What I found is that the first time the word computer was used was in 1613 by Richard Braithwaite. Then I think the next important point in computing was actually in 1622 when the slide rule was invented. So basically this allows for much more bigger calculations to be done faster than to be done by hand. And then Francis Bacon uses binary, and this is a replica of earlier calculating machine in 1623. And then I think it's also important point in 1703, which is the Leibniz binary system. That's basically the cornerstone for current computers nowadays. So this was kind of a short history of computing. Now, in modern days, what is important is actually to be aware about the Moore's law, because now we know that everyone is aware about computers, cell phones, and everything. And the power of computers is coming by the integrated circuit. How many transistors could be actually put in a small chip? And it was recognized very early in the industry that it's almost linear and grows. But there is a physical limitations how much this can go. As soon as it gets close to the size of atoms, then we'll have problems. So in this, it is anticipated that there could be that maybe we are close to the limits of this doubling every year. And in the next 5 to 10 years, maybe, we'll see that the quantum computers will take over so that this would continue as a linear or some other kind of relationship. I found that it's very nice to summarize the modern electronic age of computing with this graph where you can see some most important devices, and basically the key components like punch cards, solid state relays, vacuum tubes, transistors, and then integrated circuits. Nowadays, the computer power is compatible with the power of a mouse brain, and it seems that we're close to be the power that is the human brain. So that's why probably you notice more often that artificial intelligence is a topic that comes up again and again. It's also because of advertisements, but because also people are trying to really do something with it. And they're making progress on that with the applications in transportations and other services. So now I'll go and review briefly the history of classical physics. So again, I want to stress out some of the key important components, basically, and players like Aristotle. Then we have Galilei, who is the father of modern science, and these are some of their publications. Of course, Newton made a big push into mechanics, and with his calculus, basically became the father of modern physics, practically, theoretical physics and experimental physics. Now, Faraday, Maxwell, and Einstein, they're important because they kind of highlighted the age of electricity and magnetism. And Maxwell is considered the first one to unify electric and magnetic phenomena. And in his paper was actually Faraday, I believe, was the editor for his paper. And Einstein, he made a big leap into special relativity and general relativity. And this is the year when he had a few very important papers published. Now, interesting fact is that actually the history of quantum physics starts at the beginning of last century. It's a nice coincidence. That's kind of a key player. There are other people who are important, but basically what was happening is that Max Planck was discovering the black body radiation and the idea of quanta for energy to be able to describe the black body radiation and prevent the infinities that arise if one uses classical mechanics and classical physics treatment in explaining the radiation of a black body. Now, surprising enough, for people who are not aware, most likely everyone heard about Einstein, and they would assume that he got the Nobel Prize for his great discoveries. But eventually, actually, physics students early enough learned that Einstein got his Nobel Prize for photoelectric effect, explaining the effects why photons are ejected from materials when you shine light on that, not because of the special or general relativity, which are considered to be really his top achievements. Then some of the other important players, Niels Bohr with his model of the atom, and de Broglie with his wave mechanics. Basically, Niels Bohr introduced a nice way to explain the electromagnetic radiation that is coming from ionized atoms like hydrogen, and introduced rules that kind of explained why electron orbiting a proton is not radiating, because from classical physics, one would assume every object that is moving with acceleration should radiate electromagnetic radiation. The key component in Niels Bohr idea was that the wave that is associated with the electron should close on itself. So it should be equal wave numbers along the orbit, the classical orbit. And that's explains basically the quantization of the orbits and the energies. De Broglie's idea was that if you have a particle with a mass and velocity, then when it's moving, then this particle would have momentum, and a subatomic level for these particles would be associated wavelength. And of course, the bigger the momentum or the bigger the mass of the object is, then the wavelength would be smaller and smaller. So this is one explanation why we don't behave like quantum objects, because we are too massive for that. But where we go down to a very light object, then the wavelength becomes important, comparing the object wavelength with the surrounding environment, like in double slit experiments where one observes electron interference. So the next group of participants in this era, these are the people who coined the word quantum mechanics: Max Born, Heisenberg, and Pauli. Here their faces, kind of common pictures. And this was the push of the matrix mechanics in 1925. And it's important that Max Born realized the important feature of quantum mechanics is that observables do not commute. For example, position like the operator Q is measuring the position of a particle, and P is measuring the velocity of a particle and its mass. So if classically one measures this, it could be done easily. What is the position? What is the momentum of a particle? But quantum mechanically, people realized that this is not possible to be achieved. And that was the Heisenberg uncertainty principle. Basically quantifying quantum mechanically, there is a limit to how accurately or how precise we can measure two conjugated variables like position and momentum. And now Pauli is important, and people who go into quantum computing, they will face more and more his Pauli matrices. These are 2x2 matrices representing the spin of the particles. So X practically represents rotation around the X-axis, Y is related to rotation about the Y-axis, and Z around the Z-axis. And this is the common rotational group in three-dimensional space. But once this group is realized as algebra, the algebra, then there's a two-dimensional realization, and the Pauli matrices represent this fundamental representation of this rotational group, which is called SU2 or SO3, the rotations in 3 dimensions. So the next group of players, and this is the final batch of kind of key people that we recognize, is Erwin Schrodinger, who introduced the Schrodinger equation, which is very important way to look at quantum mechanical processes. But this is mostly for classical systems that are slowly moving and Newtonian kind of type. Dirac worked, and he was the first one to discover actually the Dirac equation, of course, and solution of the problem: how do you write a relativistic equivalent of the Schrodinger equation? And in his work, actually, he came to the Dirac gamma matrices. Nowadays, they're called on his name because he was the first one realizing their importance. But these Dirac gamma matrices are built from Pauli matrices, spin matrices. And then the next guy is Richard Feynman, and he discovered a lot of things, but one of the very important components is actually the introduction of the Feynman diagrams, which allow pictorial representation of physical processes. Also, Feynman is the first guy to talk about quantum computing. And now at this point, I want to switch and give you a little bit more about quantum phenomena.
If you have polarized sunglasses, you have a quantum measurement device.
Each of these pieces of glass is what's called a polarizing filter, which means when a photon of light reaches the glass, it either passes through or it doesn't. And whether or not it passes through is effectively a measurement of whether or not that photon is polarized in a given direction.
Try this. Find yourself several sets of polarized sunglasses or old photographic filters. Look through one set of sunglasses at some light source, like a lamp, then hold a second polarizing filter between you and the light. As you rotate that second filter, the lamp will look lighter and darker. It should look darkest when the second filter is oriented 90 degrees off from the first. What you're observing is that the photons with polarization that allows them to pass through a filter along one axis have a much lower probability of passing through a second filter along a perpendicular axis. In principle, zero probability.
But here's where things get quantumly bizarre. All these filters do is remove light. They filter it out. But if you take a third filter and orient it 45 degrees off from that first one, and then you put it in between the two, the lamp actually looks brighter. This is not the middle filter generating more light. Somehow, introducing another filter actually lets more light through. With perfect filters, if you keep adding more and more in between at in-between angles, this trend actually continues. More light.
This feels super weird, but it's not just weird that more light comes through. When you dig in quantitative...
So this was demonstrating the kind of weird phenomena, or kind of, I would say, interesting phenomena, because for physicists, everything that is not understood well becomes interesting to understand and explain it. So that's kind of the overview of the history and computing and physics, and intro to quantum phenomena. Now, the modern concepts of quantum computing, as I mentioned before, was introduced by Richard Feynman. He just mentioned it, and he thought that if we cannot really do the calculations that we need to understand quantum phenomena, then probably we need a quantum computer to do that. And then this is kind of the really very short history of quantum computing. It starts with Feynman, and key components is actually a Peter Shor algorithm for quantum code breaking. Basically, that means that you can factorize a very large number much faster than with a regular computer. Then in the beginning of this 21st century, that's the D-Wave systems that working on quantum computing. And nowadays, the D-Wave is actually the company that is much ahead of everybody else. On most of the slides, you will see about 128 and 500 qubits, but nowadays they have about 2,000 qubits. So what are the key concepts in quantum computing? We have the superposition. This is very important. Classically, you don't have a superposition. You have a slice of pizza or you have a bagel, but you cannot have a bagel pizza. And this superposition actually brings to kind of weird interpretation of quantum mechanics, like Schrodinger's cat, whether cat is alive or dead. But mathematically, what it means is that the system could be in two positions, and also it could be in any superposition of these two kind of possible states, as long as the overall probability is normalized to 1. So basically, all probabilities that a system can be observed could be added as a linear combination to describe the state of the system. And of course, measurements would determine what would be the results upon measurements. The other phenomena is the quantum tunneling. Basically, quantum tunneling is related to the fact that at some subatomic scales, particles can tunnel through a potential barrier, unlike in classical mechanics, where if you have to take something over a hill, man, you cannot tunnel through the hill. You have to carry it to the top and come back down. So you have to do work and energy. Quantum mechanically, as long as you have energy, there is some probability to go and disappear from the left side of the valley and appear on the right-hand side without having to go through the top, curing enough energy to go over. And the third phenomenon is entanglement. This is basically when things become really weird, in a sense that properties that are measured of an object at one place seems to affect the behavior and the measurement outcome in another place. This is kind of demonstrated again using the superposition. And as I mentioned, for this one can think that it's the unit circle when you're considering normalized vectors on a unit circle. So this is, for example, a vector representing a configuration of a cat that was sent to two observers left or right, and 0 and 1 represent no cat, and yes, I detected a cat. And this is more or less of a state which makes sense classically. When one observer gets the cat, the other wouldn't get a cat. But then there are other properties of objects. For example, a photon. You can have a photon with their polarization, and you can create a pair. And this pair could be sent to two different observers in a state that if one of them measures the polarization to be, for example, right-handed, then the other one would find it to be also right-handed. Or if one of them finds it in left-handed, then the other one would find it to be right-handed. For particles, it will be, for example, the spin up and spin up here. These are general states which depends on what exactly system is considered. But these are important entangled states because they cannot be specific combinations, random combinations of classical states. So this is becoming very important when one does quantum computing, because different qubits has to be entangled. So these are the three main kind of quantum phenomena that are important. And now I'll go a little bit more details about what is happening in terms of logic. Classical computer has only 0 and 1. These are what all your computers and electronic systems are doing, keeping track of zeros and ones. That means that if you have n bits, for example, then you have a total of 2 to the n power possible permutation. So that's how you can write anything on an n bits register and the number of possibilities there. And then classical computers are just processing these possibilities and coming different processes, and then the outcomes are always very deterministic unless you put in a random generator somewhere in your algorithm. In a quantum computer, the key thing is qubits, and a qubit is, as I said, like a circle. So now you have a 0 is represented 1 point on a circle, and 1 is represented with another point. But then any other state of the qubits, which is this is linear combination with a circle with a radius 1, could be represented on this circle. And specifically, here's a special combination which is like a cat that is dead or alive, for example. Mathematically, this is just a two-dimensional vector, and the components of the vector subject to the constraint that size the length of this vector would be 1. And then representing actually the different gates, the logical operations that one can do on quantum computer. The key components are the Pauli matrices, and they are three-dimensional representation usually to visualize it. So, for example, the X gate Pauli matrix, this would correspond to rotation of a sphere around the x-axis. The Y gate, this would be rotation about the y-axis, and then Z gate would be around the z-axis. Now, actual representations of these rotations would be by 3 matrices. Here, I'm just illustrating the physical realization of the process of applying a gate to a quantum computer. And this is also called a block sphere in representing the state of a qubit. If you have only one qubit, usually the operations that we can do are not operation, and that's it. I mean, you can turn 0 to 1, but classically, that's all we can do on only one register with 1 bit, because these are the states. For quantum computer, actually, there's another important gate which is called the Haram gate. And if you apply this gate, you get this superposition between 0 and 1. And if you apply the gate again, you get the state 1. So in a sense, this is kind of a square root of the NOT gate. And these are the interesting things that very often one come across. For example, the imaginary unit I on the unit circle represents the square root of -1, which is in the real numbers impossible to be identified. And in a similar way, for a classical computer, you cannot identify a Hadamard gate, which is the square root of the NOT gate. And that's the matrix representation of the Hadamard gate along with the Pauli matrices. And of course, you can have other transformations that you can do. For example, for a qubit, you can change the phase of all of your state. Whatever was the original state, you can turn a change in the phase. So after that, of course, there is a 2, 3, and many more gates and operations that generalize the AND and OR operations. But I wouldn't get into these details. I would like to talk now a little bit about the possible applications of quantum computing. One place is the quantum communications. Basically, the quantum key distribution was introduced in 1984. This is a process of using entanglement, where a photon is sent, 2 photons are entangled, and then they are sent to 2 observers. Commonly in literature, they are kind of called Alice and Dave, I think. So you have observer 1 and observer 2, and they receive their key. We have disentangled photons sent to observer 1 and 2, and when they receive the photons, they uniquely know what is the state of Bob or Alice key. So the other observer. So then the key, when distributed this way, is guaranteed that even if someone is eavesdropping and trying to get the key, basically they'll get a value that would not be accessible to Alice or Bob. That means that they immediately would know eventually that somebody was eavesdropping. So the quantum key distribution is one thing. Cryptography, this is the prime number factorization. That was the Schur algorithm, where you can actually factorize a prime number much faster than a classical algorithm. And then there is a state teleportation. It was illustrated in 93. Basically, the idea, I'll mention a little bit more, but if you have a system, then somehow you can, quantum mechanical system, you can clone the system in a way that you can teleport its state. Of course, quantum mechanically, the result is that you destroy the original system, like the fax process that we do classically. So these are some of the key applications in terms of quantum communications. Of course, this kind of applications can grow further into artificial intelligence. Basically, there is a Grover search algorithm, which is shown to be much more efficient searching general database than classical search algorithms. And this means that this may provide a better processing of large data sets. And of course, if one can turn an optimization problem into a search of the best solution, then of course, this would be an optimization problem. Pattern recognition could be viewed as a type of optimization problem. And eventually, this can all go into variety of art forms, for example, music, visual expressions, and even texts, and so on. So, of course, then there are other applications that probably no one would ever think about those days, because we don't know exactly what we can do yet, and what are the limitations of quantum computing, and what are the real applications. So let me say a few words about the quantum teleportation. So classically, we have an original that is scanned, and then we have intact original going out of the fax machine, the sender, but then the data is transmitted to receiver, which uses a raw material to generate, through the application of the received data on the raw material, the copy of the original. Now, of course, we know that the copies are not perfect, but they are sufficiently good enough for our classical purposes. The quantum teleportation idea is that you have a quantum system with its state, and then you go through the process of scanning. That means that you're using entangled pair of photons or some other particles. So one of the particles is used in the scan process of the original, and this kind of disturbs the original, scrambles the original state. But the data that is generated from this scanning is sent to receiver, that also receives the second particle from the pair, and through processing replicates actually the original. And ideally, this is exactly the state, the system exactly in the same state like the original. And of course, by the process, it seems that this would be not possible to clone things, that you keep the original and then have a replica of the original somewhere else. So that's the thing, is that although quantum computing may kind of break the code, then it will provide a ways of quantum computing communications and other applications. Here I wanted to show just the picture of the 6 people that were working on the quantum teleportation concepts. Now, the next demonstration is kind of the Schur algorithm and applications and limitations. Basically, for example, about 12 years ago, if you wanted to use a 1000 bits keyword key, you would have needed about billions of years to actually factorize this key and figure it out. If you have double the number of the size of the key, this actually increases practically the time that you need to factorize and break the key much more and more. So it's actually with the classical computer, it becomes very impossible to kind of use this linear increase in the size of the key and being able to break it. Now, of course, when you improve the computers and algorithms, then things change. For example, in about 6 years, maybe you would be able to run a computer for about 38 years and you'll break this 1000 key successfully. Or equivalently, you can wait until, for example, 22 more years, and then you'll be able to do it in 3 days. So that's basically with increasing the computational power, but as I mentioned, there's a limitation on that. And then on the right, we can see again what happens if you double and then quadruple the size of the original key. Again, it becomes the process kind of intractable once you get to the big enough key. With a quantum computer, of course, you need the equivalent qubits for the original bit system. And again, he's doubling the qubits, and the gates needed for processing and creating the circuits to process the original qubits. How many gates? And that's what we are working nowadays, basically people who are building new quantum computers. It seems that 1,000 words key, 1,000 bits key would need about 5,000 qubits and about 33 10 to the 9 gates, and this would take only a few minutes to be broken. Then again, if you double the qubits, this would increase the time, but the time is not so significantly increased as in the quantum computer. It's still in the range of minutes and hours. So this is demonstration of the Schur algorithm. If we have a powerful enough quantum computer, how it can overperform over the classical algorithm. Now, some other applications, of course, in computing, space exploration by improving the artificial intelligence and robotics, then we can explore space. We can have a better telescopes and so on. So these are more like scientific applications, but all the scientific applications are often driven by society needs. For example, health services and medicine could be revolutionized with quantum computing, where more personalized medications and drugs could be discovered and engineered. And of course, in finance, where huge data could be processed faster and more efficient, and many other kind of domain of social and human applications. Now, at this point, I would like to move now to the computational resources, unless there is any questions, or maybe I'll leave the questions towards the end and we'll come back whenever needed. So quantum computing hardware, as I mentioned, this is D-Wave, and when I talk about the resources, I mean here actually resources that are available to people in general. So you can register to the D-Wave and you can start running their codes there. And as I mentioned, nowadays they have actually about 2,000 qubits, but I believe the 100s and 500s are available to general users. IBM 50 qubits is available to general users, and then Intel just announced about 49 qubits for their processor. Google announced the 72 qubits, and Rigetti, which is kind of the startup that is quickly developing and entering quantum computing, unlike the other giants. Basically, it's developed very quickly for the past few years since startup was originated and initiated. Then it reached to 19 qubits, and they claim that it's very scalable. And of course, the Chinese are also not behind. Alibaba, who demonstrated artificial intelligence on the Stanford tests, they have 11 qubits. That's what I have been able to find on the internet. But that means that most likely they may have actually a much bigger system in their research lab. In terms of software, there is the D-Wave, and there is the IBM Q Experience, the Quantum Information Science Kit, which I really like because these are mostly Python scripts that one can explore, learn quantum mechanics, learn Python, learn quantum computing and other things. So these are really very easily available. Rigetti has Rigetti Forest, and again, that's also software and there are devices that could be run. Microsoft is focusing more on the software side. They are developing their quantum computing software. Google has their CirQ, and QCWave is a startup focusing on software for quantum computing. So this is the Google actually playground, the QCWave, and of course there was another one that I found, Kuiper Systems in Canada, the Applied Communication Sciences. Now there are other companies out there, so that would be impossible to put in a slide, but I just wanted to get a general overview of the main players. So the D-Wave, as I mentioned, it's now 2000 qubit systems, and that's how they look, and this is basically their control panel. The actual processor is isolated in rooms behind it, and a lot of layers. And if one goes to their web page, they can watch some videos and they can learn more information about the D-Wave. But this is generally how nowadays the quantum processors and the equipment around it looks like the quantum computer. This is a picture of the IBM 50 qubit processor, and they call it chandelier. Again, this is the typical similar size like the D-Wave. Now, I haven't found actually pictures of what the IBM looks like, but I found their news brochure that was explaining what are the key components. Now, the new thing that Intel is bringing is actually the spin qubits. That's different from the other components that were based on Josephson junctions and superconducting materials. Some of the problems, well, one of the important problems is the coherence. So this is related to the fact that quantum mechanically we can have a superposition, but because of interaction with the environment, this superposition would collapse to something. This is equivalent to doing a measurement, and it's often considered in the Schrodinger's cat paradox when people talk about cats whether collapses to be alive or dead for the observer. The other important thing is the error correction. Basically, if you cannot sustain your quantum state through the process and you cannot verify that it hasn't been corrupted through the quantum circuit, then you're not sure whether you're doing what you intended to really compute with your quantum computer. So this is another important domain of future development and active research. The output measurements, the process how to realize this. This is a picture from the IBM Q Experience, their representation of a system with 5 qubits, where here only 3 are active. Basically, they're created and then the quantum circuit is applied, but eventually to get it to understand what was the outcome of applying these quantum circuits on a particular state, one has to do a measurement. And once measurements are done, that means that classical registers are populated and their values are obtained. So inevitably, quantum computer would need a classical computer to interface, because we have to actually get to a point where we understand the outcome of quantum computing. And of course, a big problem is finding the right problem for quantum computers. This is actually a really serious problem, so that Rigetti have announced a $1 million prize for whoever demonstrates the quantum supremacy. That means demonstrating quantum implementation of a quantum computer that is superior to a classical computer, and therefore demonstrates the moment where we enter the quantum computing era, really using algorithms and quantum computers that outperform classical computers in specific tasks. And always the important problem is the cost. For example, the D-Wave that I showed the picture, it sold for 15 million. That means that this is about $7,000 per qubit. So this is much more than what you have for your own laptop, even a server or like a moderate machine in a university or company. So these are the problems, and then I would like to conclude my talk with saying a few things about quantum computing, pointing that basically this would be a complementary to classical computing. It's not gonna replace classical computing the same way that quantum physics is not replacing classical mechanics, and special relativity and general relativity are not replacing Newtonian mechanics. They are useful in their own domain with their tools that were developed and understood well. It will be a few more years until becoming of age. We still have to demonstrate the quantum supremacy, and therefore it is very open field for opportunities to explore. One can explore hardware development or software development or any future applications using the available tools out there. And that means that it's really a nice moment to be in life, where you can pick your favorite, explore opportunities, and hopefully you may actually find something really interesting, and you may actually build the next Apple or Intel or something else. So with this, I would like to open the floor for discussions and questions.